Hello and welcome to yet another graduate level video from Dr. Viv. Now, even though these lectures are meant for graduate students, it is fun to do problems from good undergraduate textbooks. This problem here is adapted from the Hamiltonian chapter in Taylor's book, which is used for undergraduate classical mechanics at our institution. So let's look at this problem. And then when I say adapted, I mean that I added some additional things to make the problem somewhat unique. So the first thing to note is that the pulley is ideal. Nothing is lost by making the pulley heavy, except you get complications, that's all. But other than that, you can do it for a massive pulley too. The problem as stated in Taylor's book has a light pulley. You have two masses separated by a spring of spring constant K. It's ideal, namely it satisfies Hooke's law. On the other side is a mass capital M. Now to simplify the equations, you're asked to take capital M equals 2M. It's just something that the book says you do. Then you're asked to solve Hamilton's equations for two specific initial conditions. The first initial condition is the one where at t equals 0, you fix the upper block, you let the lower block hang and stretch the spring some, and then you release everything and see what happens. Now, by the way, since m is equal to m, you can expect some sort of balance between the two sides. So we'll look at that. The second initial condition is you keep that fixed and you pull this down by a further amount. So this has got some equilibrium stretch. Let's call it x sub e, and then you double that stretch, and then you let the whole thing go and see what happens. So that's a interesting and fun problem. So I thought we should do it. Now the thing you have to do before you start is to define your generalized coordinates, because to do the Hamiltonian, you first have to find the Lagrangian. So that's going to be our first approach. Draw the pulley. Here's a initially I'll just call them M1, M2, and M3 just to be general. I always like to start generally and then input specific data. Now we're given the total length of the string. So that's going to be one constraint. The second constraint is going to be that the pulley does not slip, even though it's not said, it is understood that the string does not slip on the pulley. So these are the two constraints that we're going to have. Now, let us, however, the string slipping on the pulley, not slipping on the pulley is not very important in this problem because the pulley does not have any moment of inertia. If it did, then it would be an important constraint to consider. So we'll just focus on the string length constraints here. It would be helpful to take the generalized coordinates to simply be the position of each of these masses from the center of the pulley. That seems like the most obvious generalized coordinates. And then I have these coordinates. Did I mess it up? Yeah, that's y2 then. And that's y3. Okay. Furthermore, we'll also indicate the stretch of the spring. The unstretched length of the spring is L0. Anything additional to that is known as the stretch of the spring. Let's call that x. Okay. So we have immediately we can write some equations to form the constraints. First is y2. Y2 is equal to y1 plus the unstretched length of the spring, okay, plus the stretch of the spring. So that's like really common sense. Then we also told that this total length of the string that's draped over the pulley is constant, and that is L1. So let's write an equation for that. L1 should be equal to y1 plus y3 plus the half circumference of the pulley. Let's just say the pulley has got a radius. They've not told us the radius. We'll just make it up, radius r. Okay, so these are the two length constraints that we have. These length constraints are satisfied at all times. So what I can do is I can differentiate the length constraint. The first length constraint, when differentiated, gives me y2 dot equals y1 dot plus x dot, because L naught is not time dependent. This constraint, when differentiated, I get 0 when I differentiate L1, I get 0 when I differentiate pi r. So I just get y1 dot plus y3 dot equals 0, or in other words, y3 dot equals minus y1 dot. So that's what I get from differentiating the constraints. And it's time now for us to write the Lagrangian. But before we do that, we have to select our 0 of potential energy. It's convenient to take it to be the center line from which all the y coordinates are defined, so that above the center line is positive potential energy and below the center line is negative potential energy. Okay, now we can write the Lagrangian. Lagrangian is kinetic energy minus the potential energy in the system. The kinetic energy is the kinetic energy of each of these blocks. The potential energy has got two contributions. One is the gravitational potential energy of each of these blocks, which will be negative because it's all going to be down below the center line, plus the elastic potential energy of the ideal spring. So let's write all these things. So the Lagrangian L, and let's try to get rid of most of the variables. I'm going to get rid of y2 using this constraint, and I'm going to get rid of y3 using this constraint. So I really only have everything in terms of y1 and x. So those are our preferred variables. And why is that? Because the initial conditions are stated as initial conditions on y1 and x in both of these cases. So let's do that for that sake. So y1 dot, x, and x dot. The Lagrangian will not depend on time. So the kinetic energy is 1/2 m1 y1 dot squared plus 1/2 m2 y2 dot squared, but y2 dot is that. So that's y1 dot plus x dot, the whole thing squared, plus 1/2 m3 y3 dot squared. Now y3 dot is negative y1 dot. When I square it, I lose the minus sign. So that just becomes y1 dot squared. And now the potential energy terms. It's minus of potential energy that's already negative because it's below that center line. So it's going to be plus. So it's going to be plus m1 g y1 plus m2 g y2. But y2 is given by y1 plus L naught plus x. And the potential energy of the third object. So that's going to be plus m3 times g, and then y3. And for y3, what I can do is I can solve this equation for y3 and write here. So it's L1 minus y1 minus pi r. And don't forget the spring. The spring potential energy is 1/2 kx squared, and that has to be subtracted. So there's our grand Lagrangian. Looks pretty complicated, I think. So we can certainly simplify it a little bit, because I have y1 dot squared, y1 dot squared, y1 dot squared in 3 places. So I can write this Lagrangian as 1/2 m1 plus m2 plus M3 y1 dot squared. Now what I have done when I did that is to expand this out. When I expand this, let me write the terms I get when I expand that above here. I would have got y1 dot squared plus 2 y1 dot x dot plus x dot squared. So I've only taken care of the first term. I still have this term and that term, so keep that in mind. So let's focus on the middle. The middle term has got a 2.5. They cancel out, so I just get m2 y1 dot x dot, and then I still have this term, which will be multiplied by 1/2 m2. So I have finished all the kinetic energy terms. Now for the potential energy term. So again, I can play the same game. I can take all the y1 terms together. So y1 has got m1g, m2g, and negative m3. So I'll write that here, m1 plus m2 minus m3 times g. Why I'm taking g outside, so that's common to all three terms. And then I still have a bunch of terms. You know, for example, I have this mg, m2gx, so I have to write that. And I have this 1/2 kx squared. And then I have a bunch of constant terms. So what are the terms I've not written? It's m2gl naught, m3gl1, and m3g times pi r with a negative sign. These all are constant terms. They will play absolutely no role in the Euler-Lagrange equations. So I'm just going to call this negative u naught. Okay, I'll call it negative u naught. Now, it's a good time to substitute the given values because I don't want to keep carrying around m1 plus m2 plus m3 and things like that. It would look super awkward. So what I'll do now is use the data of the problem. M equals M2 equals M. But I always like to bring things up to this stage because if you have another problem which says that M1 is something and this M2 is something and M3 is something, you can start from this stage. You don't have to start the problem over. You can start from this stage and proceed to solve the new problem. So I always like to bring things in the most general form up to a certain point. So that's the data we've been given. Capital M is 2m, and these other two masses are just m each. So we'll keep coming back to the original sheet. I'll also explain this title to you in a moment. So let's just do the busy work. Now let's substitute all these terms in the Lagrangian. M1 plus M2 is 2m, and that's another 2m. So that's 4m divided by 2, which is 2m. So the Lagrangian is 2m y1 dot squared plus m2 is just m. So it's m y1 dot x dot. That looks like a double dot, but it's actually the bleeding from writing on the previous page. So, and then 1/2 m2 is m, x dot squared. And then here I have m1 plus m2. Okay, so this is interesting. They're kind to us. Why is the book kind to us? Because they have arranged for this y1 term to disappear. All right. That's very specific to these choices. If you did not choose things like this, that would not happen. M1 plus M2 is 2m, and M3 is also 2m, so this term disappears. So I'll just indicate that by writing plus 0. And then I have plus mgx for this term, and then negative 1/2 kx squared, almost able to fit it in one line, minus u naught, this newly minted term u naught. So what I can do now is write, the Lagrangian is finished. Let's call that the first step. The second step in forming Hamilton's equations is to write down the canonical momentum. Pi canonical. Now I would like to call it P instead of pi for old time's sake. So the canonical momentum is associated with two things. There's going to be a canonical momentum associated with a velocity y1, and there's going to be one associated with a velocity x dot. So let's do it for both of them. So y1 is going to be, by definition, del L over del y1 dot. All I have to do is differentiate. So that gives me 4m y1 plus another term with y1 dot is this one, m x dot. And then the canonical momentum corresponding to the coordinate x is del L by del x dot. Two terms have x dot, this term and this term. So I'm going to get m y1 dot minus, actually not minus, it's still plus mx dot from differentiating that. So this is the beauty, and this is why I call this a non-trivial Legendre transformation. Now this, by the way, happens in a number of problems. The double pendulum problem, if you go back a couple of videos and see the double pendulum problem, there also you have the same property. Anytime you have a Lagrangian that involves terms like y1 plus two generalized coordinate squared or 3 generalized coordinate square, you are going to get these mixed terms, and the mixed terms will produce coupled coupled linear equations. So the Legendre transformation now is no longer dividing by a constant. We have to invert a matrix. But this is a 2x2 matrix, so rather than do any fancy things like Cramer's rule, I'll just solve the system of equations. So third step is the Legendre transformation. Legendre transformation is simply a means of getting velocities in terms of momentum. Forming the Hamiltonian requires us to do this. So let's do that next. I'll write those equations again. P y1 equals 4m y1 plus mx dot. So what I can do is I can divide both sides by m, right? So I'm going to get py1 over m equals 4y1 dot plus x dot. The reason I do this is because I see the same term on both sides, so that I sense there's a simple way of dealing with this. So px is, I'll write that down again, it's my1 dot plus mx dot, which tells me that px divided by m is going to be y1 dot plus x dot. Now all I have to do is subtract these two equations. So let me call this equation 1 and that equation 2. So 1 minus 2, what will I get? So these two, when I subtract it, gets rid of the x dot term. So py1 minus px divided by m is just going to be 3 y1 dot. Okay, and this tells us what y1 dot is. Y1 dot is going to be py1 minus px divided by 3m. Now this is an important result because we have solved for y1 dot in terms of the canonical momenta. Now you have, of course, the option of putting this in there and solving for x dot, but rather than doing that, let me do the following. I'll multiply the equation 2 by 4. If I multiply this by 4, that becomes 4 and that becomes 4. And then I subtract, I'll get rid of the 4y1 dot this time. That's the only reason I do that. So 4 times equation 2 minus equation 1. What do I get? So I get 4 px minus py1 divided by m. And this time it's going to be 4x dot minus x dot, which is going to be 3x dot. So I've solved for x dot as well. X dot is equal to 4 px minus py1 divided by 3m. Another box. We have performed the Legendre transformation. Okay, the next step is to write down the Hamiltonian. What we have to do now is to use these. And the definition of the Hamiltonian requires us that all the generalized velocities be substituted in terms of the corresponding canonical momenta. So I have the Lagrangian right here. Let me just move it so we can see it. Now we'll form the Hamiltonian. The definition of the Hamiltonian is the following. H, which will be only in terms of x, px, y1, and py1, is the general definition. I'll write the general definition first. Sigma over all I, qi dot pi. So that's the canonical momentum corresponding to the coordinate qi, and qi dots are written in terms of pi's alone. Okay, minus a Lagrangian, which is a function of qi dot, possibly time, but qi dot written in terms of the pi in both places. So that's how the Hamiltonian is formed. Let us faithfully follow those instructions. All right, so that's the summation. So we have, I need all the space I can get. So I get the first coordinate is y1 dot py1 plus x dot px minus the Lagrangian, which is L as a function of y1 dot written in terms of only px and py1, x and x dot written only as a function of px and py1. So that's our terrifying object, the Hamiltonian. Now let's write down everything. y1 dot times, this is py1. Let me just write y1 dot first. y1 dot is py1 minus px divided by 3m times py1 plus x dot, which is 4px minus py1 over 3m times px. Now the Lagrangian. Minus 2m y1 dot squared I get that. Okay, so you can already sense a fair bit of algebra that's going to happen. Plus m times y1 dot times x dot, which is here, Well, the worst is almost over. And then I have this term here, 1/2 mx dot squared. And then the terms after that are just potential energy terms, but don't forget the minus sign. So I get minus mgx plus 1/2 kx squared. And my motivation to define this as negative u naught becomes apparent because now I just have plus u naught. Okay, now to simplify this, it's not too bad. So what I can do is I can multiply both this inside. So I get py1 squared over 3m minus px py1 over 3m. I'm going to write all terms separately like this. Plus, here I will get 4px squared for the first term over 3m minus py1 px over 3m. And then I'll take the 3m outside the square. So that becomes negative 2m over 9m squared, because 3m squared is 9m squared. And then I'll expand the square. So that gives me py1 squared minus 2p y1 px plus px squared. All right. And then I have this term. Once again, I can take 3m times 3m outside common. So I get negative m over 9m squared. And this time I have to multiply this into that. So let me just do it. So first this and that. Let me not talk too much. Let me just carry it out. All right. And then I have to do this term. Again, I take the 3m outside, but this time it combines with a 2 to form 18 instead of 9. So I get plus. I think I made a mistake, and that is when you have Lagrangian, put a minus sign in front of the Lagrangian, that's a minus, and that's a minus. Oh, sorry, wrong place. That's a minus. So you have two minus signs here. So that's how I get the minus sign there. And here also I have the minus sign. All right, that looks better. Minus m over 18 m squared. And this time I just square that. So that's 16 px squared minus 8 px py1 plus py1 squared. And then our potential energy terms, I'll just use up the remaining space. There. Now, let's just simplify it a little more to bring it into a nicer look. So first of all, I noticed there are several terms with py squared. Many of these m factors cancel out, so let's take care of that first. So everything is 1 over something m. So it might be useful because they all have different denominators. That's got a 3, that's got a 9, that's got an 18. Let's agree on the following. We'll just take m outside each term. So the Hamiltonian h becomes, so I'll write it as py1 squared over m times a bunch of fractions. From here I get 1/3 From here, I get negative 2/9. From here, I'm getting negative of a negative, or positive 1/9. Then I'm getting negative 1/18. Great. And then the next term is px squared over m times. So you'll notice that there's a 4/3 here. And I have a negative 2/9. That's a -4 and a minus, so that's a positive 4/9. And then negative 16/18. All right. So that's px squared. Now the middle term. The middle term, I mean the product, px py1 divided by m. What does that multiply? First of all, you notice that there's the same term twice, so that's going to be negative 2/3 because it's 1/3 and 1/3. So it's negative 1/3 and negative 1/3 is negative 2/3. And then I have negative 2 and negative 2. So that's positive 4/9. Positive 4/9. And then here I have negative 4/9. Seems like there's some mysterious cancellation here too. And then I have one more term there. That's a negative 1/9. And then 8 with a negative sign and a negative sign. So positive 8/18. And then potential energy terms, negative mgx plus 1/2 kx squared plus u0. Now, before I did the video, I put these things on Wolfram Alpha so I could do the fractions easily. And the answers are as follows. That is just 1/6. Okay, you're invited to check my work. And this is 2/3. And that whole thing is 1/3. How about that? We got the Hamiltonian in one line. So that's our Hamiltonian, since it's a major part of the problem. Let us box it. We have found the Hamiltonian of this amazing system. That's step, actually forming the Hamiltonian is a major step in itself. So the Legendre transformation I said was step 3. So let's call writing the Hamiltonian step 4. Now for step 5. Step 5 is solving the Hamilton equations. Once we solve the equations, we can then input the initial conditions. Hamilton's equations are a system of 2n first order partial differential equations. In this case, it'll become ordinary differential equations. And then we have to solve them. Okay, so that's we're not done with all this. So I'll move it over there and put back the problem statement. So Hamilton equations are got by following Hamilton's recipe. So the Hamilton said x dot will be del H by del PX. Now, these half of Hamilton's equations are a waste of time. It just recovers the Legendre transformation. It's a good way to see if you've done your work right. This is the Legendre transformation set. So Legendre transformation recovery. So let's do that. And then the other one will be y1 dot equals del H over del py1. So let's make sure we get our Legendre transformations back. To recall, the Legendre transformations are here. So I get x dot del H over del px. So I'm going to get a contribution from here and a contribution from there. So when I differentiate with respect to px, I'll get a 2. So that makes it 4px over m, 4px over 3m. And then when I differentiate here, I'll just get py1 over 3m with a negative sign. So that's going to be 4px minus py1 over 3m. That recovers the second Legendre transformation. Great. Now let's do the first one. This is proof that all this algebra was correct. If any of these fraction addings were wrong, this would show up here. Now y1 dot is given by that. Let's go and differentiate. So I'm going to get this 2 here, which cancels with the 6 to produce a 3. So I get py1 over 3m minus, with respect to y1, I get another term here. I don't get any terms there. I get a term there. So I get minus px over 3m. And that's just, let me write it again as common denominator, py1 minus px over 3m. The second Legendre transformation. So this is a good verification that we formed the Hamiltonian right. It's always a useful check. Now, the other pair of Hamilton's equations have the dynamic content. So the dynamical Hamilton equations are px dot is negative del H by del X. So let's see what that is. When I differentiate with respect to X, I only get 2 terms, one from gravity and one from spring. Mg minus Kx. Now the negative sign here cancels with a negative sign there. That's why I have positive Mg and negative Kx. Now Py1 dot is negative del H over del Y1. We initially said the Lagrangian does not depend on Y1. That's one of the great things about the Lagrangian. Numbers we chose for the masses ensured that Lagrangian, this is the Y1 dot term. So that there's no, Lagrangian does not depend on any Y1 coordinate. That's a Y1 term, not Y1 dot, just a Y1 term. So because you don't have any dependence on Y1, these are called cyclic coordinates. And so the corresponding momentum is conserved, because when you have the rate of change of momentum equals 0, that means the momentum is conserved. So that's why we say that Y1 is a cyclic coordinate. Let's digest what that means for a second. It means no matter what you do in this problem, the momentum corresponding to Y1, which is the momentum of this mass, is always conserved. Whatever it is initially, it'll remain the same throughout. Well, the 2 initial conditions we're looking at are initial conditions where this is not moving initially. If it's not moving initially, it'll not move ever. So that's what is guaranteed. Okay. So we'll write those observations down. Therefore, Py1 is constant, but both initial conditions imply that Py1 is 0, since M1 is held fixed. If m1 is held fixed, the momentum it had in the beginning is the momentum it has for all time. So this tells us that Py1 must be 0. So what we can do now is use the Legendre transformations again. Those Legendre transformations do encode some important information. Since Py1 is 0, we can look at the Legendre transformations and see what happens to them. So they become the following. X dot is, because Py1 is 0, it's just 4/3, 4 over 3m px. And the other Legendre transformation is this one. Y1 dot is equal to negative px over 3m. What I can try doing is differentiate them again. So differentiating with respect to time, I'm going to get x double dot equals 4 over 3m px dot, and but px dot, so this is why I differentiate again, because I have px dot here, it's right here, mg minus kx, but px dot is mg minus kx, so I'll substitute this into there. Therefore, x double dot equals 4 over 3m mg minus kx. That's looking pretty important. Now let's differentiate that next. So differentiating again, I get y1 double dot equals negative px dot over 3m. And again, using px dot equals mg minus kx, I get negative 1 over 3m mg minus kx. So these differential equations for y double dot and for x double dot can now be solved. We can solve for x as a function of time from here. So if I divide m into that equation, I get the following, x double dot, let me call this equation 3 and equation 4. So I'm looking now at equation 3. X double dot plus, I'll bring this term over to this side after dividing both sides by m. So I'm going to get plus 4k over 3m x. And here, when I divide by m, the m's cancel out. And so that's equal to 4/3 g. Now I'm going to define a natural frequency, omega squared, which is 4k over 3m. That is the appropriate frequency to define in a spring oscillator, spring block oscillator system. This tells me that omega is the square root of 4k over 3m. Let's box that important angular frequency that comes up in this problem, just like that. Now that's just a simple harmonic oscillator, x double dot. So I'm going to get something like x double dot plus omega squared x. If I had x double dot plus omega squared x equal to 0, that's just simple harmonic oscillation. It's not equal to 0, it's equal to some constant term 4/3 g. So all you would have to do is add a particular solution. The particular solution to this problem is just mg upon k. So x particular is just mg upon k. Let's verify it. I get it by just looking at it, but let's verify it. If I differentiate twice, I'll become 0 because it's a constant. So I'll just have omega squared times x equals 4/3 g. Let's verify if that's true. Omega squared is 4k over 3m times x particular, which is mg upon k. And what is that? The m's cancel out, the k's cancel out, and that's indeed 4/3 g. So that's the particular solution which I simply guessed. In all these problems, you just guess the particular solution. And then the general solution is equal to the full solution is equal to the solution of the general homogeneous equation with a 0 on that side, which is just sines and cosines, and the particular solution, which is this one. Okay, so we'll write the general solution down. Therefore, x of t is the particular solution, mg upon k, plus normally the general solution for a simple harmonic oscillation is cosine omega t plus some phase phi. So we'll call it some initial x naught cosine of omega t plus phi. This initial phase phi needs to be determined, sometimes called the phase angle. Now, let's look at the initial conditions. I'm looking at the initial condition set number 1. Let's recall what that initial condition set is. At t equals 0, the upper mass m is held fixed at y naught. We already used that, and released from rest. So if it's held fixed, this is stretched to equilibrium length. So that tells us, the first initial condition tells us that the stretch x of this mass of the spring is just going to be the equilibrium stretch of the spring. So that's the important information we can get. X of 0 is just xe, equilibrium stretch. Now, how do you find the equilibrium stretch? Under conditions of equilibrium, let's draw a little free body diagram for the mass m. Under conditions of equilibrium, the spring force, F sub s, will be exactly equal to the force of gravity, F sub g. That's what equilibrium even means. So let's impose that. F sub s at equilibrium equals F sub g. And so that tells me that k times x equilibrium, because the force, the magnitude of the force, Hooke's law is negative kx, but we're looking at the magnitudes here, is equal to mg. And that tells me what x sub e is. X sub e is mg over k. So x of 0, which is that thing here, is actually mg over k. So now we can write our full solution. Therefore, so let's implement the initial conditions. X of 0, which is x sub e, which is mg over k, is equal to that with t equals 0. So that's going to be mg over k plus x naught cosine phi. Because when t equals 0, you lose the omega t term. So what is this? This is actually a fancy way of finding what phi is. So the first equation we have, because mg over k cancels, is x naught cosine phi is equal to 0. Let's call that equation 5. I hope my numbering is consistent. I think we have up to 4 now, so that's equation 5. Now the other thing, it's not enough to just say the cosine phi is 0. You can't just get phi from that. Remember, cosine gives you 2 solutions, one in the first quadrant and one in the fourth quadrant. So we also need the velocity data. At t equal to 0, everything is held fixed. So we also have x dot equal to 0. Let's implement that. If I differentiate both sides, I get x dot equal to 0, and then derivative of cosine is negative sine, but I also pick up this omega term. So that's negative x naught omega sine omega t plus phi. That is x dot as a function of time. Now, at x dot at time 0 is 0. So now let's put that initial condition in. So I get 0 equals negative x naught omega sine phi, which means that x naught sine phi is also 0. Let's call this equation 6. The only way you can satisfy these 2 equations, because sine and cosine are generally different, is if x naught is equal to 0. Therefore, x naught is equal to 0. Now that's a pretty remarkable conclusion. If x naught is equal to 0, this means that x of t is just mg over k. There is absolutely no oscillation. And that kind of makes sense. If you hold everything in equilibrium and let it go, they'll still be in equilibrium. There's no reason for this to go any place. So that's the reason why it came out in this manner. But it's a good test case, even though it's kind of obvious now that nothing should happen. It means that our equations actually work. And the second initial condition will be slightly different, of course. So everything remains the same at all times. Now let's go back to the y equation. That was here. Let's look at that. Y1 double dot is negative 1 over 3m mg minus kx. And x is that. So that's going to be negative 1 over 3m mg minus mg, because kx is just the same as mg. So that gives me 0, which means that y1 dot is just the initial velocity, and the initial velocity is 0, which means that y1 as a function of time is also just the fixed length y naught. So nothing happens here either. So the Hamiltonian method passes with flying colors, because if you release the system from rest, nothing should happen. That should remain how it is. That should remain how it is. Nothing should happen. So the first initial condition is just a a smell test, if you will. So the system is robust and the first initial condition works. Second initial condition is more interesting. Here you will have action because you're monkeying with the second mass. You're pulling it further by some distance. So let's see what happens. The same equations will have to be used. So IC number 2. Here at t equal to 0, x is 2x sub e, and y is equal to y naught. Now I'm going to go back to this equation for x, because these equations are valid for any initial condition, and see what happens. So x as a function of time is given by that. So x at 0, which is 2xe, which means it's going to be 2 mg over k, is equal to all of this. X naught cosine phi. So that tells me that x naught cosine phi is equal to mg. Over k. Well, that's good to know. I think that's equation 7 now. Let's now differentiate this with respect to, we've already done that somewhere, I think. It's right here. So let me substitute for that at time 0. So x dot 0, we have been told it's held at rest. So that's 0. And that should be all equal to negative x naught omega sine phi. Now x naught is not 0, so the only way this x naught is not 0 because of that. So the only way this can be satisfied now is if sine phi is 0. So now we are forced to conclude that sine phi is 0. Okay, the easiest solution of sine phi is phi equals 0. So let's choose that and substitute it there. If phi equal to 0, I'm going to get x naught times cosine of 0, which is 1, equals mg over k. So therefore, x naught equals mg over k. Now I can finally put this back in this equation and write my answers. Therefore, x as a function of time equals mg over k plus mg over k times cosine of omega t plus 0, which is just omega t. So we have a beautiful equation. Let me write one more step. X of t equals mg over k times 1 plus cosine omega t. Pretty non-trivial looking. The only other equation I need is y1. Once I have x and y1, I get everything else because all other quantities are defined in terms of x and y1. So look at y1 double dot. It's this one here. Let's grab that equation. Y1 double dot equals negative 1 over 3m mg minus kx. That's k times all of this. Mg over k, 1 plus cosine omega t. The k's cancel out. So I can also cancel out the m's. All right. This mg will cancel out that mg. So that I don't lose a constant term. So I just have mg, negative mg cosine omega t, which cancels with the negative sign. So at the end, I just have g over 3 cosine omega t. Beautiful. All you have to do is integrate this twice. Integration of a cosine is not difficult. You just get, is it positive sign or negative sign? When I differentiate cosine, I get negative sign. So when I integrate cosine, I get positive sign. All right. So first integral, y1 dot is going to be, but each time you integrate, you also have to divide by the constant that this multiplies. So I get g over 3 omega sine omega t plus the initial condition, y1 0. But the initial condition is that you hold it fixed. So that's 0. Then you integrate again. So I get y1 equals g over, oh, well, the integral of sine is negative cosine. So that's negative 3 g over 3 omega squared, because I'm pulling down another omega to the denominator. So I get cosine omega t plus y1 0. Well, what was the initial stretch? Y1 0 was simply y naught. I believe the statement of the problem, the upper mass is held fixed at y naught. So that little y naught there is what we are looking at. So that's just equal to y naught. Okay, now let's see what we get. Now I just have to, that's it, that's the answer. So y1 as a function of t is equal to negative. Now I'll substitute for omega squared. Remember, omega squared is 4k over 3m. When I do that, I lose the 3 and the 4 comes instead, and then the m goes upstairs. So that gives me negative mg over 4k cosine omega t plus y naught. So this is beautiful. We have solved the problem in its complete generality. That's y1 as a function of time, and that's x as a function of time. And should anyone ask you, what about the other masses? What happens to them? You just have to tell them, well, look at this. So this tells me that y2 dot equals y1 dot plus x dot, and y3 dot equals minus y1 dot. So you can immediately answer them. And so you can tell them, oh, y2 dot is going to be y1 dot, which is this. So this actually tells me that y2 is equal to y1 plus x plus constant, but y2 is also held fixed. So the constant is y2 0, let's say. That's the initial length of y2, which is going to be given by this. Initial length of y2 is y1 0, which is just y naught, because y1 0 is actually y naught. Okay, so the initial length is y naught plus L naught plus xe. Okay, so that's going to be y naught plus L naught plus x sub e, which is mg over k. That thing is mg over k. So if you really want to write this down, take a couple minutes to do that. It's going to be y1, which is negative mg over 4k cosine omega t plus y naught plus x, which is here, plus mg over k, 1 plus cosine omega t plus y naught plus L naught plus x sub e. And you can simplify that. I can already see mg over this reacting with that, and you can simplify it. Okay, so I'll write here, can simplify. Let's integrate this. If I integrate this, I get y3 equals negative y1 plus some constant, which I'll call y30. What is y30? Y30 is going to be y naught, which is the initial length of this, and the string length is L1. So y30 is going to be L1 minus y naught minus pi r. All right, so we can write our y3 equation. It's a negative of that, so that's positive mg over 4k. And just box this too. Cosine omega t. Now, because that's a minus, that'll be a minus y naught. But minus y naught will cancel with, well, actually it won't, it will add. So I'll write minus y naught plus L1 minus y naught plus minus pi r. And again, you can simplify that. The only simplification you can do here is to add the two negative y naughts and make it 2 y naught. So not much of a simplification. It's almost the final answer. In this way, we have solved the problem in complete detail. That is, we have given the location of each mass as a function of time as the system evolves with time.